Thank you, everyone who's joining us. I see you all filtering in. We're going to give people just another minute or so, and then we'll get started. All right, welcome. Thank you, everyone, for being here today. I'm Sarah Brewer. I'm the director of our education program at Accords. I want to welcome you all to our program seminar today. For those of you who are new to us or might be attending one of your first seminars, I want to share a little bit about what Accords is. So we're the Adult and Child Center for Outcomes Research and Delivery Science. We are something of a one-stop shop for pragmatic research at the University of Colorado Anschutz Medical Campus. We do pragmatic research. We receive various types of, for faculty to receive various types of services and supports for grants and projects. We provide incredible mentorship, training, and education in health services research. And you can see some of these offerings here. This particular series, we are partnered really strongly with our biostatistics and analytic core. So I want to highlight them today. And you can see some of our upcoming seminars here. So in March, we have the next in this series with Ryan Peterson and Catherine Colborn talking about statistical learning from data to interpretable insights. Our other current seminar series is on ethics challenges and messy decision making. And we have a panel coming up on March 6th, and the next in that series is April 3rd. And then we have two in-person guests joining us in April and May in the statistical methods series. So we hope you will mark your calendars and join us for that. We also partner really closely with CCTSI Community Engagement Corps, and in April we'll be hosting a community engagement showcase, again an in-person event, and we hope many of you will join us here in the Anschutz Health Science Building to meet some of our community partners and researchers working in community. We also have the Colorado Pragmatic Research and Health Conference coming up June 5th and 6th. Registration is open for that, and abstracts are due March 1st. So if you are hoping to attend and share some of your work as well, know that that deadline is coming up. Okay. And then finally, our D&I science program is hiring a dissemination implementation scientist. If that is one of your areas of expertise, we hope you'll take a look at our posting and consider joining us. Before I introduce our speaker today, just a couple of little housekeeping items. First, use the chat throughout our talk today. I'll be monitoring and we'll have time for question and answer at the end of the hour. And then second, take a minute at the end of our talk today to share your input, your feedback in our evaluation. That helps us to continue to provide the best seminars and educational offerings for all of you. Today, this seminar is part of our series on statistical methods for pragmatic research. It's the 6th out of a 9-part series, and we welcome Rashelle Musci today. She is Associate Professor of Mental Health in the Department of Mental Health with joint appointments in the Department of Biostatistics and the Department of Population, Family, and Reproductive Health within the Johns Hopkins Bloomberg School of Public Health. She's a quantitative methodologist with expertise in latent variable methodologies, longitudinal cohort studies, cluster randomized trials, data harmonization, and prevention science. We are very pleased to welcome you today, Dr. Musci, in your presentation on latent class analysis, assumptions, and extensions. Welcome.
Awesome, thank you. All right, I'm gonna go ahead and share my slides. All right, so thank you all for joining. I'm going to move my slides over here so I can see them better. Thank you all for joining me today. I'm excited to talk about latent class analysis. This is a topic that I think a lot about, and very excitedly talk to a lot of students and early faculty, mid-career faculty, and senior faculty about, and think about the best ways to answer really important questions using latent class analysis. So I wanted to spend a little bit of time talking about my background so you can sort of understand a little bit about where I'm coming from and how I think about the use of latent class analysis. I did most of my schooling at the University of California at Davis, really focused on human development or quantitative psychology. And that's where I really got a basis for trying to understand how we can use latent variable methods in research. And then I did my postdoctoral training over at Johns Hopkins, partially in the School of Medicine and partially in the School of Public Health, really thinking about how we can take latent variable methods and apply them to solution-based research. On a day-to-day basis now, I spend a lot of my time sort of in the world of prevention science. I am an associate editor for the Journal of Prevention Science, which is the flagship journal for the Society for Prevention Research. And I'm also on the board of directors of the Society for Prevention Research, where I think a lot about training aspects and the best ways that we can train future prevention scientists. And then in terms of research, although it is quite, I have a lot of research going on, but I wanted to highlight three that I think are really important to think about as we're sort of walking through latent class analysis. So the first is the Baltimore Generations project. This is the project that I will be using as an example later in the talk. I'll present a latent class analysis that we did utilizing that data. So this is a multi-generational study that looks at the longitudinal impact of a prevention that was done in early childhood. And so we're bringing the participants of that early intervention into our lab with their offspring. So we're really sort of building out this longitudinal data set in a really lovely way. The second project is a data harmonization project, which I think is likely to be some really interesting areas of research in the future. I think NIH is getting increasingly interested in ways that we can capitalize on data that's already been collected and they've already paid for. So in this project, we're harmonizing data from 6 randomized controls trials that were focused on a school-based intervention. And followed their participants up into adulthood. And here we're trying to see about the impact of that intervention on sort of crossover effects. So things that the intervention weren't originally designed to target. So in this case, we're looking at suicidal outcomes, internalizing symptomatology, and psychosis as our primary targets. And then finally, something that some of you may know about because of some data collection that is happening at your university. I'm a part of the Data Analysis Center for ECHO, which is the Environmental Influences on Child Health Outcomes. The goal here is to harmonize data from existing cohorts to understand the environmental impact of sort of exposures on child health and development. And there, I'm really trying to figure out the best ways that we can utilize latent variables to answer these questions. So like I said, I'm going to be talking about an example later using data from the Baltimore Generations project, which I'm excited about. All right, so let's first step back a little bit and talk about what exactly latent class analysis is. So the primary goal of latent class analysis is to really think about the ways in which we can group individuals in meaningful but data-focused ways. From a more pragmatic point of view, essentially, it's just a series of logistic regressions, which I think really simplifies things for folks. So the goal is for us to really find how people are both similar and different based on a given set of indicators. And so we're grouping people based on their subpopulations or sort of an unknown group, and trying to identify the group of individuals that they sort of best fit within. People often pit latent class analysis against factor analysis. They say that latent class analysis is person-centered, whereas factor analysis is variable-centered. I want to sort of step away from that narrative a little bit and think more about the latent class analysis as a tool in and of itself. So it can be a way that we can group individuals based on how they're responding to particular indicators or items on a scale or categories of variables. When we're thinking about a modeling framework, I always use this picture because I think it can be really helpful to sort of separate the different types of modeling that we do within latent variable modeling. So if you've seen any sort of latent variable education before, this might seem familiar to you. So this is sort of the framework that we're working in, where circles are indicators of a latent variable and squares are indicators of a manifest variable, or one that is measured. And so here we're going to be talking mostly about a categorical latent variable with categorical indicators. And so that truly is a latent class analysis. If we were to shift this a little bit and think about a categorical latent indicator and continuous indicators, then that would be a latent profile analysis. But for the purposes of what we're talking about, we can consider them very similar to one another. One thing that I won't be talking about in great detail today is something called growth mixture modeling. So this is where we're thinking about trajectories of a particular symptom or behavior, and trying to estimate latent classes of those trajectories. The format of what I'm going to be talking about is quite similar, and I have some sort of steps and resources later in the talk for those of you who are interested in learning a little bit more about growth mixture modeling. So when we're thinking about latent class analysis, this is what our analytic figure is going to look like. It's pretty simple. We have our categorical latent class variable sort of indicated by that circle with the C inside of it. And then we have our indicators of the latent class. So those are those U's. In this case, that's indicative of it being a binary indicator. So we can have a series of them. In many cases, it can be something that is continuous that you make binary, or that is sort of binary in nature. And we're basically saying that this latent construct is measured by these manifest indicators that we're including here. So I would be remiss if I didn't have a single formula in this entire talk, even though I generally don't like to include them in these types of talks. But I wanted to, in this case, because I think this can be a really easy way to think about latent class analysis. So in this case, when we're estimating a latent class model, we can consider that that relationship between our latent class variable and our indicators, our binary indicators, are simply a logistic regression. And so when we have our binary indicator, which is coded as a 0 or a 1, then the conditional probability of what we're trying to estimate here is simply a logit. So at the end of the day, what we're going to be doing when we're estimating our latent class model is a series of logistic regressions. When we pull it back a little bit and think about when we've got continuous indicators, it is very much similar to this. It's just a simple regression. So in this case, it can be a little bit less intimidating when we're thinking about the estimation of these models, when we think about it as just a series of logistic regressions. So when we're sort of deciding that we want to estimate a latent class model, the first thing that we're going to do is fit a series of latent class models with increasing numbers of latent classes. We'll start at 1 and work our way up. And At each run of our model, we're going to capture information from the output in order to assess model fit. On the left here, you're going to see a set of things that you're going to look at to assess statistical model fit. So how well your data is fitting the model that you're putting into it. So the first thing we're going to look at is our log likelihood. We'll also look at Bayesian information criterion, or BIC, the Low-Mendel-Rubin test, which in M+, a pretty common latent variable software, is called for with the TEC 11, as you see here. The bootstrap likelihood ratio tests, which in M+ is called for with TEC 14, and our standardized residuals. Another really important thing to consider when you're fitting a latent class model is trying to get a sense about the model usefulness, because there's no real reason to decide on a certain number of classes if those classes are meaningless to you as the researcher trying to use this in your studies. So we really want to take into consideration the substantive interpretation of each of the latent classes in the sort of model fit decision making. The other piece of it that we want to consider is our classification quality, or how well our latent classes are sort of putting people into those classes. And we can do this through looking at classification tables and entropy. So all this to say is we're going to be capturing a bunch of information about each of our latent class models and really taking that complete picture into mind once we decide the number of classes. When you're doing this with real data, so not one that is simulated to make really lovely fit statistics, much of the time you will see that these fit statistics are going to disagree with each other. And so when that happens, you really have to rely on the substantive interpretation of these models. Inconveniently, for the example that I'm going to be presenting in a little bit, there is some disagreement there, so I'll walk you through how we decided on the number of classes that we decided on. Okay, so how does it all work? Once you run, you sort of decide on what your model is going to look like, you write the code, and the model starts estimating your latent classes. The way that it works is through the EM algorithm, or expectation maximization algorithm. The goal here is for the program to randomly put people into latent classes and then iteratively put people into different latent classes so we can improve our sort of classification. Your best classification, what the program ends up with, is the best log likelihood value. And this is where we sometimes see error messages associated with our model fit if it's not going as well as we want it to. And so in that case, we generally go back to the drawing board and think a little bit more carefully about the variables that we're including in our model or how we're estimating the model. So we're basically giving the statistical program, whichever one you choose, a bunch of information about how to estimate these models, and it's going to be iteratively walking through sort of the grouping or classification and trying to find the very best fit that it can. So a couple of practical issues, which I think are very important to consider. The first and probably the most common question that I get when people want to do a latent class analysis is sample size. This is going to be a really not satisfying answer for a lot of people because there is no easy tool that we can use to decide the number of individuals we need for a latent class analysis. So there's no rule of thumb in terms of the number of indicators and the number of people. And in some cases, the bare minimum that I've seen not so successfully done is 20 people, which I highly don't recommend. But in general, we're going to be utilizing simulation work to really support and determine the number of participants we need for a particular latent class model. I have some resources for that later, but they will not be nearly as satisfying as you want them to be. And there's certainly no sort of calculator or easy software that we can use to help determine the number of participants. It is important to know that the sample size and sort of the the distribution of your indicators are going to really influence the type and the number of latent classes that you're able to extract from your sample. So the smaller the sample size, the less classes that you are able to successfully extract from your model. So that can be really important when we're thinking about replication later on, and sort of interpretability of those latent classes. And certainly the model in which we're setting the indicators, and the model that we're setting up is going to indicate or determine the way our classes are going to look. And so there's some nuance there in terms of how you allow your indicators to relate to one another, and the correlation that you're allowed to estimate there. So that is to say that there's a lot of small nuance here. So in determining the number of participants that you would need for something like this. And for the most part, I say it doesn't hurt to just try to run a latent class model, and you'll find pretty quickly whether it's going to be a successful model run. So we're going to walk through an example here from my existing work. This is from a paper that's already been published, so you're welcome to read through that if you're interested in it. But this was sort of the flagship paper for that first study that I talked about, the main goal of which was to understand whether self-control estimated or measured in first grade would be predictive of outcomes in early adulthood. And the idea here was that we were going to try to see heterogeneity that existed in self-control as measured by a teacher report, and then look at predictors in adulthood. So I'm going to walk you through the estimation of that latent class model, and then the methods that we use to look at those outcomes in adulthood. So as I talked about before, the Baltimore Generations study, the primary goal here is to leverage data that existed already from a pretty specific cohort that existed in Baltimore City. So these kiddos were in first grade in 1993 in Baltimore City public schools. And then they were randomized to be a part of a trial that was implementing something called the Good Behavior Game, which is a sort of classroom management prevention program that's targeted towards aggressive and disruptive behavior. So we had some hypotheses about whether this particular intervention could have some impact on self-control or sort of self-regulation. And so here we're utilizing data that was collected in 1993 at the baseline of the study, and then when these initial kiddos were in adulthood, sort of the 19 to 25-year-old follow-up. So a little bit of detail here. So we had 678 participants at that original trial back in 1993. They were all from pretty specific Baltimore City public schools. They happened to be on the east and west side of the city. Most of them were Black, which is a pretty standard in the Baltimore City public schools at that time. 68.3% of them were eligible for free or reduced lunch, which was the primary indicator for sort of economic status used in this study. And then this is like a shocking thing for a lot of people, but the adult follow-up for this particular study was about 80%. It's continued. The data collection is ongoing for this, the original trial follow-up. So they've done a really great job of retaining and following up these individuals into adulthood. And then the original study really focused on data collection from self-report, from parent report, and teacher report. They used a variety of measures in this study, only a portion of which we're capturing and I'm going to be talking about today. And then I'm also not going to be talking in great detail about the intervention. If you're interested in that, I point you here to Ialongo et al. 1999. This is where the original PI of the trial talks in great detail about the intervention and the impact of the intervention sort of more proximally. So when those kiddos were still in sort of primary school. Okay, so for the purposes of what I'm going to be talking about today, we're going to be utilizing teacher reports of self-regulation. This is using the teacher observation of classroom adaptation, or the TOCA. This is a pretty common measure that we use for sort of a variety of behaviors and symptoms as measured by the teacher. It's really focused on, um, in this case, a lot of self regulation, inattention, impulsivity type measures. Um, and in this case, we're using this in a continuous fashion, which probably hurts the heart of a lot of people who like sort of keeping things on their original scale. But for the purposes of what we were trying to do, it made the most sense to think about this in a continuous way. And then in adulthood, here we're looking at a series of outcomes, um, primarily measured by self-report of the individual. But we do have some sort of public record information here. But we're capturing on-time high school graduation, college participation, teenage pregnancy, some substance use disorder, or meeting criteria for that, whether they were incarcerated, and then any sort of criminal justice involvement. Those last two were captured directly from the criminal justice system records. So we started by fitting our a sort of a series of latent class models. And here I'm not showing you the fit statistics for the single class model. It's not terribly informative. But what you see is 2 through 5 classes. We're capturing things like the log likelihood, the BIC, the low Mendel-Rubin, and sort of entropy in the smallest class. And so if you look here, typically when we're thinking about the BIC, we want to find an elbow in the values. So we're trying to find sort of the lowest point, or the point at which the number is not decreasing substantially anymore. And if you look at this, you see that there's a pretty decent jump from 2 to 3 classes and from 3 to 4. And then we see that it goes a little bit back up in the 5th class. So if we were to graph this out, you would see that elbow around the 4-class model. So the BIC is here pointing to a 4-class model. If we turn our attention over to the LRT, or the likelihood ratio test, what you see here is that there's some interesting things happening. We see significant findings here for a 2-class and a 3-class, and then at 4 and 5, it becomes non-significant. For this particular fit statistic, we like to go from where it becomes non-significant and go 1 up. So this would indicate that we should be choosing a 3-class model. So now we have a BIC and an LRT that is conflicting. We then can turn our attention over to the entropy and the smallest class. Some rules of thumb here is that we like to have above a 0.9 entropy. So this would suggest that there's some pretty decent classification quality here. That's sort of across the board what we're seeing. So we're pretty happy with that. We shouldn't use entropy as choosing our exact number of classes, but in this case, the highest value is at a 2-class model. So it's basically saying that we have very lovely separation in these latent classes at the 2-class model. Then if we look over to the smallest class, there is a rule of thumb that would suggest that you shouldn't have any class that's less than 10% of your sample size. So in this case, even when we get down to a 5-class model, our smallest class is just over 10% of our sample size. So this would suggest that this model and this sample could fit or could handle at least a 5-class model. So in my lectures, when I'm able to like walk around the room and have fun conversations with folks, I usually make people guess as to the number of classes we decided here. We can't do that here, but I will just give you the tagline here. We ended up with a 3-class model, and that's primarily because of substantive interpretation. So what happened was I laid out this particular model to my research collaborators, and we looked at the way the latent classes looked. and determined that the three-class model was really what showed some really nice substantive interpretation. I'm going to show you what that model looks like here, and it's sort of clear why we get to this point. So what you see here is the indicators on the bottom axis. So we have some sort of self-control indicators on the left-hand side, some inattentive indicators there in the middle, and some hyperactive indicators on the right-hand side. We really tried to group those indicators based on sort of the types of behaviors the teachers were reporting on. And what you see in that solid black line is the majority of the sample fit within what we called a high self-control class. So though they are showing really high levels of sort of self-control items like paying attention, working hard, and staying on task, and then they're showing low levels of sort of inattentive and hyperactive items, things like being easily distracted, their mind wandering, can't sit still. We then see some interesting separation there in the middle. And so we have a really lovely inattentive self-control class. Conveniently for us, this really nicely mimicked ADHD subtypes. And so it was sort of a nice fit for this particular model. So that inattentive group that you see there are showing moderate levels of sort of self-control items and high levels of inattentive items. So they're having trouble waiting for turns and being easily distracted, their mind's watering, and they really are sort of struggling a little bit to sit still. And then in contrast, we see this inattentive and hyperactive group. That's the one that's sort of the solid gray line. These are the individuals who are showing the lowest levels of those good self-control behaviors like concentrating and pay attention, and the highest levels of sort of the inattentive and hyperactive ones. So they're always on the go, they're interrupting and intruding, they're blurting out their answers, they're really struggling with that impulsivity. And so when we saw this sort of layout of the three-class model, we decided that this was the best and most substantively interpretable fit for our latent class framework. So from here, we decided to then move on to trying to estimate and figure out what happens next. So moving beyond our measurement model of our latent class analysis to creating a more structural model. And so we do this in a variety of ways. The primary example I'm going to be talking to you about today is when we use a latent class variable as a predictor of an outcome. But you could also think about it the other way, and you can have predictors or covariates predicting latent class membership. I'm going to be talking about it only in one way, but it's pretty straightforward to think about it in the other way as well. So what we're going to be doing here is taking our measurement model, which is our latent class model as in our indicators of behavior, and extending it out to be able to understand how self-control in childhood predicts outcomes in young adulthood. And so we do this here pretty simply by adding this structural component onto it. In our case, we're taking our binary outcomes of interest in individual models and estimating that relationship. Now, the important thing to consider here is how we do this estimation. In the literature, there's been a variety of ways in which people have done this. I'm going to be walking you through sort of what I consider to be the most rigorous way to do this, but you will find a lot of different ways in the literature. I'm going to urge you to not use a couple of them, and I'll talk about why in a minute. But this can be where we can introduce a lot of bias and a lot of misclassification in our relationships here. And so we need to be really careful about the way that we add on this structural component. So the two methods that I'm going to talk to you about that are the sort of most rigorous is sort of the automatic methods that utilize in software code to assess these relationships. I often say that this is a method that you can use if you're just trying to understand what's going on, but it shouldn't be the final method that you use. And then the 3-step methods that we're going to be talking about in more depth today allows you to have a little bit more control over the relationships that you estimate. The important thing to consider here is that our models are going to be accounting for the fact that our latent variable is latent and has measurement error associated with it. So that means what we're going to do is keep everything in the latent framework rather than pulling things out of the latent framework so that we can really account for that measurement error. We're going to be doing this in our example here through BCH weights, but you can also do it through logit methodologies. So the BCH method was developed originally by Vermont in 2010, and then some additional simulation work was done in 2014 to sort of create this new method that was then implemented in a lot of the latent variable software that we use. Essentially, what this methodology is doing is allows us to estimate our latent classes and a series of weights associated with them so that we can reflect the measurement error that exists within that latent class, and then move forward with a structural model wherein class shifting does not occur. So one of the most common things that people struggle with latent class models is that every time you estimate a new latent class model, classes can shift a little bit. And maybe what was class 1 is now class 2 and vice versa. So in this method, we constrain everything to be the same so that that model that you have and you estimated your latent classes will stay the same. This particular method is not perfect. It does have some challenges, but in general, it performs really nicely when the variance of your outcome variable of interest differs pretty substantially across your latent classes. There are some cases where this methodology won't work terribly well, and in that case, I always recommend the use of the logit method. So the BCH method is the method that I utilized for this particular project in order to look at the impact of latent class membership on those outcomes in adulthood. And so here are sort of the results of what we found. So on the left-hand side, you see each of our individual outcomes. These were all estimated in models individually. So we're treating each outcome as separate from one another. And you can see in that the sort of second column, the proportion of individuals experiencing that outcome in the full sample, and then the percentage of individuals experiencing that outcome in each of the latent classes. What we found here is that self-control measured in early childhood was a significant predictor of on-time high school graduation, college participation, criminal justice involvement, and teen pregnancy. And this, I don't really think that what we found here was incredibly revolutionary. It's not surprising to think that your self-regulation skills early in childhood would be sort of impactful throughout the duration of your developmental course, and certainly impact your ability to function in things like graduating on time and going to college. But the goal here was to really see this sort of extensive long-term impact here. So this was a nice way for us to build out this measurement model and structural component to then look at some more complex relationships later on. So that's sort of where we stand currently in the literature. It's relatively straightforward to find and estimate these models. And there's a lot of statistical software that will allow you to do that with relative ease. I'm now going to turn a little bit to talk about some of the what I think are the cool advances in latent class analysis, to give you a little bit of sort of where I think the field is going, and what I think you should consider as you're potentially integrating this type of methodology into your research. So the first one that I think is probably the most important is something called confirmatory latent class analysis. Um, as more and more studies have utilized latent class analysis in the past, we're growing a lovely body of literature that will then allow us to use that information to help guide what our latent classes look like in the future. And so the sort of screenshot here that I pulled from an article was sort of the step through a confirmatory latent class analysis. Um, it essentially allows you to utilize prior information from the literature to help determine what your latent classes are going to look like. And you still have to fit a series of models and determine the best fitting model, but you do that based on a set of prior information. And so I think as we're growing bodies of literature that utilize this methodology, this can be a nice way that we consider utilizing that literature in ways that sort of point to a particular class structure. The other advancement that is often very challenging for me to wrap my head around, but I use quite often because of my school-based work, is multi-level latent class analysis. So this can be incredibly useful if we're interested in trying to understand how latent classes transition from the individual level to whatever level two is. In some cases, it could be at the school level or at the community level. The example here that I'm showing you on screen is from Henry and Muten from 2010, which has a really lovely tutorial with beautifully written code to walk you through the different types of multi-level latent class models. But what you can see in the figure on the right is the idea that we can create latent classes at level 2 measured by latent classes at level 1. And this can be a little bit tricky to think about sort of in depth, but what you can see in the different sort of colors of this bar chart is that there are 3 different latent classes at level 1. You can sort of be designated as a non-smoker, a moderate smoker, or a heavy smoker. And then they've created latent classes at level 2 on the community level to sort of estimate high use communities and low use communities. So you can see how we can expand out with nested data the use of latent class analysis to answer some more complex questions about what's happening at level 1 and at level 2. So I think this will be really interesting, particularly for those who sort of work more deeply in nested data. And then the most annoying advancement, or I don't know, useful, I suppose, is the idea that we're trying to get better at being able to test and handle instances of measurement non-invariance. I would argue that a lot of researchers sort of put their head in the sand when we think about measurement non-invariance, but I think it's really critical to think about it, particularly with latent class analysis. So this example here is one in which we step through the process of testing for measurement invariance and differential item functioning across a couple of different factors for a latent class model. And I wanted to point out a couple of things here since some folks might be unfamiliar with measurement invariance. Essentially, measurement invariance is this idea or sort of this property that measurement is the same regardless of specific covariates that exist. So that means that the measurement of your latent class model is the same regardless of your sort of responses to particular covariate categories. And this can be particularly relevant depending on the types of latent class models that you're interested in estimating. For that previous example, it was particularly important when we're thinking about the estimation of a latent class model for sort of aggression and victimization when gender is a particular factor based on the type of model that we're using. And what that looks like for a latent class model is something like this. So on the left-hand side of the figure, this is just a simple latent class model with covariate or X predicting latent class membership. So we've got a sort of a relationship between our covariate and our latent class model. And then on the right-hand side here, you see how that covariate can have an impact on every single one of those indicators. So here we're not just creating a relationship between our covariate and our latent class model, but we're also looking at and estimating the relationship between our covariate and our indicators of interest. And so this methodology for a very long time has been pretty tedious. And so people have been thinking more deeply about the ways in which we can automate this process or make it a little bit more straightforward. This has been done in factor analysis for a while. There's some automated processes that can happen within M+ or other statistical software. And there's also some additional packages that you can use to estimate things all at once. So we're working right now on trying to create those same sort of one-stop estimation processes for latent class analysis so that we can make this process a little bit less torturous and laborious, so that more people can think about ways that we can handle measurement non-invariance. And then some additional considerations that I want to talk about, and that is statistical power. We all know that statistical power is something that's really important to consider as we're building out our sort of proposals and frameworks and thinking about sample sizes. In order to be successful at sort of a power calculation for latent class mixture modeling of any kind, we really have to rely on simulation studies that either we do ourselves or other people have published, or some prior work that has sort of used similar sample sizes and similar methods. So on the right-hand side here, I pulled a table from Kim 2012, where they nicely sort of walk through some different sort of indicators here to pay attention to, things about missing data, the number of classes, the number of indicators, and the number of participants that exist, and sort of giving a little bit of a ballpark in terms of required sample sizes. I wouldn't necessarily consider this to be the exact gold standard. There's a lot of leeway in a bunch of different ways. And then the Dizyak 2014 also goes through some simulation work. His work has specifically focused on latent class analysis and latent class regression, but you could surely use that simulation work to help support some sort of suggestions for sample sizes. The other option is then to also consider utilizing prior work that was able to find a certain number of classes in a particular sample size. That can be a real nice way to say, like, it is possible to be able to estimate 4 or 5 latent classes within a given sample size. And then the last thing I wanted to talk about was some common software and sort of packages that you can use to estimate some latent class models and beyond. So some of these can also be used for other latent variable modeling. The one that I talked about in most depth today was M+. This is a very powerful tool to utilize for latent class modeling and beyond. I'm biased because that was the program that I was trained on, but I certainly think it's a lovely and useful tool. There's also a host of free and relatively robust tools in R. So Lavon is probably the most commonly used, and there's also some sort of structural equation modeling packages that exist that are pretty powerful. You can also use Stata to estimate latent classes and structural equation models. I don't necessarily know a ton about the defaults that exist within that program for that particular analysis. So you have to look deeply about those before you decide to use them. A less commonly used one, but pretty powerful in and of itself, is something called Latent Gold. And then finally, you can also estimate latent classes with SAS. So if that's your preferred software, it's pretty straightforward to do it in that program. There is a relatively robust latent variable community out there. So if it's something you're interested in digging a little bit more deeply in, there's certainly lots of resources that you can find out there to help sort of guide you in the process. And I believe that is all I have. Thank you so much for joining and listening to me.
Thank you, Dr. Musci, for sharing your expertise with us. We do have some questions. I'm going to combine a couple of them and hope that you can maybe briefly give a little bit of distinction between latent class analysis and some of the other available but different methods. So some things that have come up in the chat: structural equation modeling, factor analysis, cluster analysis. How is this one unique and distinct from some of those other approaches?
Everyone's gonna hate my answer. It's just they're all this essentially the same type of information, but or the same type of analysis, but you're putting different information into the model. So a structural equation model is essentially a bunch of regressions. And so what you can do with a structural equation model is utilize latent class analysis within it. If you want that to be one of the variables within your big structural model. But when we think about latent class analysis versus factor analysis, we often think about the sort of result that you're going to get. So with factor analysis, what we get out of it is factor scores that we can use to understand how individual items sort of fit together. And then we can see the value that a particular participant gets or group of participants. Whereas latent class analysis is going to group individuals. So I can say that this sample has 3 groups and a portion of them are in group 1, a portion are in group 2, a portion are in group 3. It is very similar to cluster analysis. It just utilizes a different estimation framework and treats that latent variable, that latent class variable, as latent with measurement error associated with it.
Great. Thank you for a brief version of those distinctions. We have another question from Kristen that I think is really important for people thinking about maybe exploring this. You had 12 indicators in your sort of example set there. Is there a sweet spot on like how many indicators you should be looking at? What's too high? What's too low? Are there rules of thumb?
Yeah, so there's the biggest rule of thumb is that you can't have basically n minus 1 classes for indicators, right? So if I have 5 indicators, then I can only estimate 4 latent classes. So that is an important rule of thumb, particularly if you've got a lot of heterogeneity that exists in your sample. On the other end, there's no real rule of thumb, but we do want to be thoughtful and use sort of theoretical backings for trying to understand which indicators to include. And there are a number of sort of post hoc analyses that you can do to sort of constrain or pare down the number of indicators. But I always tell folks to start with the most inclusive list and then pare down as you go.
Excellent. We have another question from someone I suspect has been to a few of the other talks in our series. But can you talk about sort of the relationship between sort of your data quality, potential missing data, using things like multiple imputation? Where should that fit into your process? Should that go before or after something like latent class analysis? How do you approach that when you don't have perfect data?
I love this question. No one has perfect data. So I just I'm going to put that out there. So many of the software that we use, and M Plus in particular, uses something called full information maximum likelihood, or FIML. because we really like to make acronyms for our names. So FIML is a tool that essentially is going to use imputation to fill in missing data for the indicators of the latent classes. So that means that I can have missing data that exist on those indicators, and I can still estimate a latent class probability for a given person. Generally, I suggest to rely on that full information maximum likelihood to fill in those missing datas for the measurement model. And then I suggest after that to utilize multiple imputation to fill in missing data for covariates of interest. And in some cases, maybe moderators. I would urge against the use of multiple imputation for outcomes of interest. But you can sort of think more thoughtfully about where you want to utilize multiple imputation. But it is pretty straightforward to be able to implement that within many of the software programs that I talked about today.
Excellent. If anyone else has questions, please feel free to raise your hand or drop those in the chat. We have one other question, and I think you've talked maybe around this, but Risha asks, it seems as though omitted variable bias would be particularly impactful in latent class analysis. What are your rules of thumb in terms of ensuring that you have the relevant variables in your data set?
Oh, it's so hard. I think a lot of it starts with making sure that you're very clear about the latent construct that you're trying to estimate. So with a lot of folks that I work with, I always make them start with drawing me a picture and being able to very clearly label what's inside that circle. What is the latent construct that you are trying to measure? Is it self-control or is it something else? And in a lot of cases, that will help guide the type of indicators that you're looking at. Now, most of the time, you're not going to have all of the indicators that you want. You certainly could have, you'd be pretty limited, particularly if you're utilizing secondary data. So in some cases, you have to be pretty constrained with what you're including, and that may shape or shift what you can call that latent construct. And so you have to be a little bit careful about sort of what your labeling process is like and sort of how thoughtful you are in the inclusion of those indicators.
Dr. Musci, thank you so much for talking through this wonderful example and giving a really graspable explanation of this approach. For those of you who are still on with us, I hope you'll take a minute to fill out our evaluation, share what you think about our series so far, and we hope to see you at some of our upcoming seminars this spring. Thank you so much. Have a great afternoon.